Hello, my name is Luis Mar Avalos, and today we're going to be doing the AP Physics 1 second semester FRQ question number 1. Here in this scenario, we have a constant continuous force of F exerted on a dart of a mass of small m in a horizontal direction as it moves through a tube of length of L. It then hits a block of a mass of big M and then travels a distance of d before it comes to a stop because of friction. In the first part A, it asks, should the student use a longer tube or a short tube to make the stopping distance the longest? I would say you should use a longer tube in this case, because if you have a longer tube and we know that the constant continuous force exerted on the dart when it is inside the tube, that means that F is going to be applied to the dart for a longer time. And since F is equal to ma, that means that the velocity is going to increase the more it's in that tube. So if it comes out, it's going to come out way faster, which means it's going to embed, and then it's going to take more time for the same coefficient of friction to slow down this system. In part B, on the internet, a student finds the following equation used in similar experiments. It is asking, does this equation have an expected dependence as reasoned in part A? In which I would say yes. Here we see that D is dependent of L, the length of L. If we increase L, that means the distance, the stopping distance, is going to increase as well. So yes, it is independent. In part C, it is asking, should the students use a dart with large mass or small mass to make the dart block stopping distance the longest? This, you would say you would use a small mass, because if it is a smaller mass, that means that the acceleration is going to be greater, which means that the velocity is going to be greater. And as it goes inside, the velocity is going to take more time and more distance to stop the system. All right, so provide an accurate sketch of the following graphs while the dart is traveling through the tube. Take a right to be positive. So taking the right to be positive, then that means that the acceleration that means that the acceleration has to be continuous, like it says here, constant continuous force F, and then we have F equals to ma. So F has to follow A and vice versa. The velocity, I'm assuming that it starts at 0, so we're going to put it right here and then go straight up, because since our A is positive, then that means the velocity has to increase. Our X, displacement, has to be a parabola like this, because since velocity is increasing and A is increasing, that means that it has to go swoop up. P is momentum, and since P is equal to mb, that means it's going to follow the same sort of graph as V, which is similar with F equals ma. So it's going to be something like this. All right, so then now we have the same scenario with some values right here. Calculate the speed of the dart immediately after it leaves the tube. So we're going to try and find for V right there. We know that F is equal to 20 newtons. I'm going to write part E right here real quick. Quickly, I'm going to convert the masses right here. So we have 20 grams. So we're going to have 20 divided by 1,000. That means that M is going to be 0.02 kg. And we're going to have big M right here. We're going to do 30 divided by 1,000, right? We're going to have 0.03 kg. Okay? Calculate the speed of the dart immediately after it leaves the tube. Since F is equal to ma, I'm going to set 20 equal to 0.02 a. And with that, we're going to do 20 divided by our mass right here. And so we get our acceleration is 1,000 meters per second squared. Okay, after we do that, I'm going to use common form. Oh, shoot, sorry. I'm going to use common form to calculate the acceleration after it leaves the tube. So VF, or I'm going to use in terms, V is equal to the square root of 2a, and then we're going to put L right here. V is equal to 2 times 1,000 times the length of L, in this case is 0.5, which I'm going to put 1/2. The 2 and the 1/2 cancel out. So we're just going to have a V of 1,000 or square root of 1,000. We do it right here. We have B is equal to 31.62 meters per second. So yeah, so the speed of the dart immediately after it leaves the tube is going to be 31 meters per second. For part F, we're trying to find the speed of the dart block system immediately after the collision. The dart block system is going to be an inelastic collision because they couple together. So it is going to be mv equals to m plus big M. In this case, I'm going to do VF. In order to isolate for VF, or the final speed after the dart block system, it's going to be mv all over m plus big M equals to VF. We plug in our values right here. We have the velocity right there, and then times the mass of the smaller one, or the dart. And then we're going to do 0.02 plus 0.03, right? And then the VF after the collision, or immediately after the collision, is going to be 12.65 meters per second. For part G, derive an expression for the acceleration of block dart system as it travels across a distance in terms of the given variables and physical constants. There's no other force besides Fk when it's traveling D. So we're going to do, that's part G. We're going to do net force is equal to Ma. We're going to do the x direction, obviously, because it's horizontal. Then it's going to be Fk is equal to Ma. And then Fk, in this case, is going to be mu k times Fn equals to Ma. And you may be wondering, oh, what is Fn? Fn is going to be Fg. Because there's no other external y or like something pulling it, that means that Fn, the contact force, has to be equal to Fg in order to not go up and down, obviously. So I'm just going to immediately expand Fg. So I'm just going to do Mg equals to Ma. And then we're going to cancel out the m's. And then mu k times g is equal to A. As I travel across the distance in turn. All right. So yeah, this will be our final answer for part G. Using conservation of energy, calculate the speed of the dart block system the instant it leaves the table. So we're trying to find the speed right here. So in this case, I'm going to use, we're going to have Ke I minus work of Fk, because it loses energy as it travels the distance of D, equals to Kef. Now you may be wondering, oh, why don't you use potential energy? Well, either way, the system has not yet left the table right here. So either way, if I put PE on both sides, they're gonna cancel out. So that doesn't really matter. I'm gonna expand everything right here. 1/2 mbi squared minus, I'm gonna expand it to what we derived over here. Mu k, or work is force times displacement. So we're gonna do mu k mg times d equals to 1/2 mbf squared. As you notice, m's all cancel out. And then we're gonna have 1/2 vi squared minus mu k gd equals to 1/2 vf squared. I'm gonna immediately go into vf. So we're gonna have vf is equal to the square root. This is gonna be vi squared minus 2 mu k gd. Quickly plug in the values. Vi in this case is gonna be the vf we derived up there. So we're going to do that square minus 2 times mu k, which is 0.14, times d, which is 0.5, so 0.5. And then we're going to click enter. And then we have our final velocity right before it leaves the table is going to be 12.6435. As you can see, it kind of lost like a little bit, but not a lot. So that's pretty good. Meters per second. So that's part H. Part I. How far distance horizontally will the dart block system travel before striking the ground? So we're trying to find, as it goes right here, we're trying to find, boom, this X distance right here. I'll put like a little. Oh yeah. In order to find that X, I'm going to set up displacement. So delta X equals VIT. VI in this case is going to be the velocity as it leaves, because there's no vertical component or vertical Y. So we can immediately assume that the VI is going to be this horizontal velocity movement. I'm going to put it in terms of X, and then we're going to have the V. So we're going to be the VI to be 12.643. I'm going to just put ... times T. To find T, we're going to have to use delta Y equals to 1/2 GT squared. There's no BI in this VIY in this case, because like we established earlier, it's moving horizontally, so there's no VIY. This right here, it's not accelerating in the X direction, so we're not going to have the, we're not going to have the AT square. We're not going to have this bit for delta X. So, again, manipulate it, divided by G equals to T and square roots. And we're going to plug in our values. I'm going to change up the variable real quick. It's 2. We're going to do H over G equals to T. So over here we got 2 times H, which is 10, divided by 9.8. So T is going to be equal to 1.4285 seconds. Now, we're not done yet. We still have to plug this back into here. So I'm going to multiply it, my answer times my velocity. We're going to have our X, after we plug that in, it's going to be 18.06 meters. Last part, J. Calculate the speed of the dart block system the instant before it strikes the ground. I'm going to use conservation of energy, which will turn us into common form, but, you know. So we're going to have PEI plus KEI equals to KEF. And then I'm just going to go cancel them out already. So 1/2 VI squared equals to 1/2 VF squared. All right. And then I'm going to multiply the 2 over. So we're just going to have VF is equal to 2GH plus VI squared. VF, I'm plugging my numbers already. So we're going to have 2 times, I'll put that in parentheses, 2 times 9.8. Always important to have your parentheses, okay? 2 times 9.8 times H. H is 10. Plus our VI as it leaves the table. So our VI is this value up here. Then we're going to square that. And then we're going to get our VF to be 18.864 meters per second. And that's going to be the speed of the dart block system the instant before it strikes the ground.